Hi, this is Boris, and Jasmine and I are here from Facebook, and we're going to be talking to you about our effort to port FBOSS, which is our network operating system, to run on top of SAI, and as well as the sort of testing methodology we took for vetting the results. So before we get into the details of how we worked with SAI, I think it's useful to just sort of quickly cover the FBOSS architecture, sort of introduce what it is that we're doing at all. So FBOSS is the agent that runs on each of our network devices, and it consists of a few kind of high-level components, the most important of which are software switch and hardware switch. Those are the ones being developed by the FBOSS team. And so software switch is the hardware independent logic that sort of is the same regardless of what hardware we run it on. Whereas hardware switch is specific to the particular forwarding platform, whether it's an ASIC or really anything else that would be forwarding packets. And that has to be aware of particulars of vendor SDKs, the underlying ASIC hardware, and other considerations. The hardware switch then directly talks to whichever vendor SDK we're using to properly configure or program the ASIC. So where we use SAI will come into that picture. So why do we even want to use SAI? Like, that is a complete picture. FBOSS is widely deployed. It's sort of running our data center. So suppose, like, if we were interested in using more than one ASIC in that architecture, we have to implement hardware switch a different way for each different vendor SDK. So if we have, K vendors, then we have to have K hardware switches. And each of those is like a pretty substantial amount of effort to implement to bridge that gap between high-level networking concepts and low-level SDK calls. So we want to leverage SAI, which is sort of a standardized, generalized version of an SDK, is a way to think of it, to reduce that effort for us to onboard new ASICs. And another big advantage we could get from it is that we can kind of provide vendors a predictable target that they could look at, use, test against, right? If FBOSS is open source, and if it runs on top of SAI, you can just, if you're a vendor and you implement SAI, then you can use our test framework and you can use our application to see if FBOSS would run on your hardware, and that could kind of, that could be a target for you. So here's the revised picture, where instead of hardware switch, we have like a single SAI switch that's the same on different types of hardware. And then the vendor SDK obviously now has to include an implementation of SAI, and otherwise the architecture is unchanged. So next I'd like to talk about where we're at with this, kind of what is our progress. We have forwarding at L2 and L3 working on various hardware platforms, on more than 2 or 3, and as well as some other networking features like queuing, hashing, multipath, and kind of the list is growing. We've got the team working on catching up to the rest of the features that are supported by FBOSS. We're bridging the gap and getting them all supported with SAI switch. As for our experiences, right, we wanted to share how this went for us. I would say they were quite positive. We've really enjoyed working with SAI, and the key reasons that it was good for us were, first of all, that it lived up to its the expectation, and it really does port well. We were able to write code on one platform and relatively easily get it working on a different platform. And there are some little specifics here and there, and we'll talk about those later, but I really want to stress that broadly we were able to reuse the same SAI switch code across different vendors, and that's what we were looking for. The other kind of positives that came out of this is that we were able to really benefit from the regularity of SAI. The definition is actually quite clean, and it's well thought through. So we were able to leverage its regularity and its structure to kind of have some cool design effects in FBOSS. I want to move forward here to what exactly did we do with this regularity? Well, we were able to build a library to wrap the SAI APIs in C++ and get ourselves a bunch of benefits, particularly in compile time checking and ergonomics. And I'll give an example. I think that'll illustrate it the best. And it's sort of zoomed out. This should also have a feeling associated with, not just like analyzing the code line by line. Like sort of, if you look at it, you can tell the difference. This is the C API, and you're sort of, the important thing to point out is that, hopefully you can see my cursor, that the ID of an attribute and the value that we're setting, those are kind of coupled by the programmer and not by the type system. And here's our C++ example that does the exact same thing as that previous slide. You can see it's already kind of like easier to, it's less code, right? So it's a little more ergonomic, but the most important thing is that the enum values and the types are sort of baked together, so you can't screw up and like use the checked enum incorrectly. So you get this sort of like compile time safety of C++ over C. Like we've been able to build that library, and it's only possible because SAI was so regular, because of the attribute and object model. Another thing we were able to do, thanks to the regularity of SAI, is abstract our Warmboot implementation. So FBOSS has an important feature for our deployment called Warmboot, which is that we're able to restart our software, the FBOSS software, without touching the underlying hardware tables. So this lets us do releases of our software hitlessly without affecting the underlying servers attached to the switches or connections between routers. And so how we do that at a high level is that we replay our software switch state, in that earlier architecture picture. We're able to replay the software switches state while sort of idempotently kind of like skipping that which is already in the hardware. And currently that's like the trickiest part of our code, and it's sort of something every new person has to really ramp up on and takes a while to get, and there's lots of mistakes there. So with Scistor, and specifically with SAI, we were able to generalize this idea of reloading the existing state and then replaying our application on top of it into like a well-contained single library, which we call Scistor. And that library makes it so that you just write your sort of application logic about your networking features, and we can kind of use the magic of SAI's regularity to automatically implement Warmboot for you. Now, of course, it's good if people still learn how it works, but they don't have to like remember to do it. They don't have to fiddle with the details of these reload and replay concepts, and this really will save people a lot of time and heartache. And again, it's only possible because of SAI's regularity. I do want to touch on a few negatives briefly, and those are in under specification and inconsistency. So I'll just dive right into under specification. We felt that there was still some opportunities in SAI to document the exact expected behavior sort of more forcefully. The concepts are pretty self-explanatory if you're familiar with networking. You can kind of bring them back to what you're already comfortable with, but exactly how the like edge cases work is not always like fully fleshed out. And so we found ourselves like running it to see how it worked, running it on a different platform, talking to vendors, like sort of trying to figure out like what's the common denominator rather than being able to refer to some spec as like the truth. And even in situations where it is better specified, these things are sort of scattered. There's a pipeline document PDF, there's a spec markdown README file, there's the header files themselves. There's Word documents that outline the sort of design flow, the kind of what the group has worked on as they design SAI. But as an application developer, you end up kind of having to stitch all these different things together, and it's kind of confusing. So we felt there was room for a more robust spec, like think more like RFCs and less like, you know, just code documentation. And as well as like sort of centralizing it may be helpful. In inconsistency, I think that sort of comes from under specification, but we can list a few examples where like the porting wasn't totally free. Like we said it ports, but we had to do some stuff. Like this is where that comes in. Like what is that stuff? Well, sometimes a SAI adapter for one vendor and a different vendor like will behave differently on the same input. Like what if, you know, if you try to modify a port while the port is up, some vendors will reject that modification, some won't. How do you send a packet to CPU? Is it with the CPU port object, or is it by using the packet action to CPU? Those kind of differences. There's often, and this is by design, you know, a vendor might not implement some API, but they also might not implement an attribute of an API they do implement. Or they might not implement one operation on top of an attribute on an API they implement. Like they might not let you set a field even if they let you get it or create with it. So we found that the differences in vendors on what exactly sort of cross-product or set of actions, attributes, APIs, and all of those that they support were not always exactly consistent, and we kind of, it became a little painful to manage all that. And finally, there's defaults that vary from system to system, whether something exists by default, like a bridge or a VERF, whether you need to unprogram something and then reprogram it or create it from scratch. Like that's been a bit inconsistent. It came up in a few other areas like queues and hashes. Yeah, but largely, you know, we were able to port it. And so now I'm going to hand it over to Jasmeet, who's going to talk about how we were able to reuse our testing from our existing system for testing the new system.
Hi, this is Jasmeet. I'm a manager in the net system in the FBOSS team. I'll be talking about how we are testing the FBOSS switch. Right, so testing SAI switch. We have over the years built a lot of features and use cases for FBOSS. FBOSS has been in production for 6 years. So over this time, we have added a lot of features. We've added a lot of functionality and a lot of edge cases that we've tackled for our network. We've put into this code. So our goal here is to validate that we do the same thing with SAI, we don't regress. And luckily, we've over the years built up a comprehensive set of tests, which we run every day to validate our native hardware switch, that it's not regressed in any way, shape, or form. So we want to port those to SAI, and we want to port them in a hardware agnostic level, at a hardware agnostic level, so that we can run it for both our native and our SAI switches. Aspirational goal here is that if a SAI adapter passes our SAI hardware test and benchmarks, FBOSS is able to run on that. It's called aspirational because not every part of the FBOSS stack is covered, so I'll highlight which ones are not covered, but substantially the functionality is covered by these tests. So as I said, every aspect of ASIC programming is tested by the 700 plus and growing tests and benchmarks. This serves as a validation for FBOSS code, for vendor SDKs, and for new ASICs. So when we get a new vendor SDK, when we get a new ASIC, the first thing we do is we try to make the test pass on this, and so that we know the functionality is intact. We use it daily and on per commit basis to qualify trunk, to qualify the FBOSS releases to push to our fleet. So it is heavily in production use. The nice thing about these tests is that they are self-contained. They are run on a single box FBOSS device. They don't need any topology and any cabling to set them up. They don't require a complex setup, and they can do data plane in themselves. There are some clever tricks we use that I will talk about later that we will go through. All of them exercise Warmboot, or large percentage of them exercise Warmboot. Warmboot is very important to us because we update our software pretty frequently in the fleet. Our goal is to do once in every 2 weeks, and we cannot tolerate any outages or drain capacity for doing this. So each test can be thought of as in 2 functional blocks. There is a setup block which programs the ASIC, sets up things as the test wants, and then there's a verify block which then does the verification. As an example, think of a load balancer test which verifies ECMP and hashing, where the traffic is supposed to spray evenly on the ECMP links. The setup functional block would program the ASIC, program the hardware ECMP group, set up the hashing, and then the verify block would pump traffic through it and verify that all the links are evenly balanced. So on a cold boot iteration, we would run the setup and verify blocks. On a warm boot iteration, we would warm boot and just run the verify block. The assumption here is that the ASIC and our SDK and our state comes back exactly the same as it was before after a warm boot. Link programming and protocols are not tested as part of this stack because we have separate tests for link programming, and they require somewhat more complicated setup. And protocols are tested heavily via unit tests and via emulation. So we use containers to test those, and necessarily ASIC does not need to be involved in this. This is a logical view of how things look like. The hardware test links with the vendor SDK with the FBOSS code is embedded in the hardware test. There's a CPU port here. The ports are put in loopback mode, and this is logically represents a FBOSS switch. So talking about data plane is a pretty important thing to verify here. We use the switch as its own traffic generator. Heavily used ports in loopback mode, as I just showed. The way we kind of think about this is, if you take a step back, there are only 2 sources of traffic to a switch. The CPU, which is very easy to create in these tests, where you just craft a packet and inject it into the into the switch pipeline, and it then goes through its normal processing. And then the other source of traffic is from front panel ports. This is where loopback ports come in pretty handy, where we use what is called as a pipeline bypass mode, where you can use this on the switches to bypass the pipeline and just send the packet out of a particular port. So now what we do is we use this to send it out of a front panel port. Since this is a loopback mode, the packet loops back and comes back to us. Now it's as if the packet came back on the front panel port and will inject into the switch pipeline as if it came in via front panel port, and will behave, the traffic will behave as if it came on front panel port. This works for most of the test cases. I would say 95% of the test cases are completely satisfied by this. There are some test cases, however, that do need line rate traffic. Example, costs. For this, we create data plane loops. And the way we do this is, remember the ports are in loopback mode. So what we do is we program a next hop whose MAC is set to be our own MAC. Now when we inject a packet, the packet loops back, comes back to us, and then we do the same routing decision again because it's our MAC. It will go out again with that next hop, and then it'll loop. However, this loop only goes maximum up to 255 times because there is a TTL decrement on every iteration of this. So you can only do CPU into 255 times the traffic. This is not sufficient to create line rate. Luckily, there is a knob in the SDKs or in the chips that we've used where you can disable TTL decrement on a next hop basis. and do this one. Now when you do the packet injection, if you disable the TTL decrement, this will create an infinite loop and hits line rate pretty quickly. We've had this proposed in SAI and it has been upstreamed, so it should be available in the subsequent SAI specs as well. The line rate traffic becomes interesting to test costs, as I just mentioned. A couple of examples of tests we use to verify this. Think of two, queues on a port, one which is in weighted round robin, weight X, and another with weighted round robin, weight Y. We inject packets and seed the Q1 with weight X, then another packet for Q2 with weight Y, and then we will check in a few seconds what the traffic looks like, and it should be weighted. The traffic weight distribution should be X to Y between those two queues. You can do the same thing with strict priority versus weighted round robin, where the strict priority queue should smother the traffic on the weighted round robin once the strict priority queue is seeded with this traffic. The benchmarks use the same setup as hardware tests. They are used to verify low latency operations, which are pretty critical to us: ECMP shrink, and then TXRX rates on the slow path. Warmboot exit path is all tested benchmarked via these operations. Then also we do the large scale and high throughput operations, which is bulk route add and bulk route delete, which we measure and quantify on each everyday basis via these benchmarks. A quick demo. I have a test running with SAI here. This is on a Trident 2 box. I'm running what is called a hardware load balancer test. I'll run this here. This is pumping V6 traffic. As I talked about, you will see this running ECMP traffic on a full hash algorithm. So it's programmed the full hash, which means that it's programmed the hash to use SIP, DIP, and source port dashboard. Then the CPU traffic simply means that it is sending traffic from the CPU. There's a corresponding front panel iteration of this test as well, which I'm not going to go through, but as you kind of like look at this, it goes through and programs the route, programs the ECMP group, then pumps traffic. And here is where it's verifying. So it verifies that the deviation between the most lightly loaded link and the most heaviest loaded link is within a tolerance level. We've set 25% here. The max deviation here is 5 point some percent. So it's checking that these are satisfied. That was it for the testing part. There is a few call to actions. We have open source and we are heavily investing in this open source of our SAI test and benchmarks. So we have pretty extensive instructions on how to build this, how to run this against your adapter. If you think your FBOSS, if your ASIC and SAI adapter and SDK can support FBOSS, please give it a try. We are trying to make this as simple as possible for new vendors to experiment. There is code for SAI libraries and benchmarks is open source here. You can check this out. And for us, we want to contribute to SAI API and SAI Store and keep cleaning them up. These are very much work in progress. We are iterating on this pretty intensively. And as I said, we are investing heavily in our open source build and user experience. So if people try this and want to engage with us, we are welcoming these requests. Thank you.